The question we get asked a lot is, how long should I make my speaker cable? How long should I make my interconnect cable? Well, the generic answer is what? Speaker cable's short, internet cable's longer. Why? Nobody ever asked me why. So once they go home, eventually they call up and said, why am I doing this? What's the reasoning behind this? So today I'm just going to kind of go through why that is. And a lot of the test data on actual cable will explain why we do that. Now, the first thing we need to realize is when we make a cable long or short, why are we doing that in the first place? Why is it even a question? Just do whatever you want, right? The amplifier doesn't want you to do whatever you want. Amplifiers test the best into a 3 ohm resistive load in stereophile. When you put a reactive load on an amplifier, their linearity changes because you're altering the voltage and the current with respect to time. That amplifier is trying to chase that around. Something weird happens in amplifiers when they have to chase phase shift, all right? Not all amplifiers react horribly to it, but some amplifiers will become unstable if you put too much reactance on their output. Your interconnect cable also has, by the way, an amplifier that drives that cable. A lot of people think an interconnect cable somehow is magic and only your amplifier driving a cable to your speaker is, quote, an amplifier. But you have a voltage amp on your interconnect and it has the same kind of problem. It's looking at a reactive load they really don't like. So when you put loads on the back of your cables, you automatically are making your amplifier or your I/O device less happy than if it was a purely resistive load. People say, well, then just make it a resistor. Well, today I'm going to explain to you why that can't be done by anybody, at least not anybody that's immortal here on Earth. We have to just deal with it and sort of sneak around it and make things work as best we can. This is the Cliff Notes version of a very complicated topic when you design an amplifier. It has to do with things called Laplace transforms. Anybody here an engineer? If you say you like Laplace transforms, I'm going to kick you out. They're miserably difficult to work with, but working with them correctly, they will tell you how much reactance you can put on a design of an amplifier based on how you've designed that amp before it does one of two things. It flat oscillates, it's no longer an amplifier, or it has what's called overshoot. Some people call that ringing. And that ringing can be heard and can be tested in the audio band. A lot of people will say, well, gee, I thought that was way out at RF. I didn't know capacitance mattered on a speaker cable. How many people have heard, only worry about inductance on a speaker cable because we have 30 amps or more spiking through our speaker cable, so inductance is the big alligator. The little minnow is capacitance. Don't have to worry about capacitance. Well, the reference is first order filter roll-off, right? Our cables are a filter. But if you put your cable characteristics out there and Google an equation for first order filter roll-off, you're going to find out it's out in the many, many tens of hundreds of megahertz. So people say, capacitance isn't that important on a speaker cable. But it is when it makes your amplifier have overshoot or ringing in the audio band. It doesn't roll off your high frequencies, no, but the capacitance drives your amplifier crazy, all right? Now, if we look at what real cable does, this is actually a graph of two different cables, and it's showing the impedance with respect to frequency. As you get to these lower frequencies, what's happening? Our impedance is going up quite a bit, and that's due to the nonlinear behavior of speaker cables' velocity of propagation through the audio band. The other thing you notice is here's the phase over here on this axis. We got zero phase out here at RF. Down here at the low frequencies, all of a sudden our phase is going to 40 degrees or more. That's called reactance. All of our cables will exhibit this behavior. No speaker on Earth will not go to purely capacitive reactive properties at low frequencies. It's just how the physics works, guys. You can see slight differences in the middle here depending on the design of the cable, but they're all going to wind up at roughly minus 45 degrees, which means it's a capacitor. They're all going to go down here to 0 degrees out here at RF. Now, when we look at RF, and a lot of people want to pretend our audio cables are RF, they aren't. If you look at RF, a lot of people say, well, the equation square root of L over C, right? And you go, yeah. And a lot of people say, well, So it has to have L and C, and the next guy will say, no, it doesn't, because L and C, you don't have any phase shift, and the definition of impedance is a reactive component combined with a real component, right? So if I have no phase shift at RF, why do we call it an impedance? Well, theoretically, you're both right. You have to have L and C because your impedance is a ratio of L over C. It's there, but they cancel once you get out to RF, and I have some test data to show that on both types of cables, speaker and interconnect both. But long story short, our cables aren't RF cables that look resistive. So if you take your Ethernet cable or you take a 75 ohm CATV cable and you plug it into your electronics, it's actually going to a 75 ohm resistive load on a circuit board. No reactance whatsoever. It expects that cable to be at RF, so it acts like a resistor, even though it has L and C, because that's, of course, what determines the impedance. But the cable itself at RF does not have any reactance. Our audio cables, unfortunately, have lots of reactance as we go down in frequency. And that reactance is what your amplifier has to deal with. It has to somehow come to terms with that and not ring or oscillate when it's trying to design your speaker. And by the way, the amp doesn't see your cable. It sees your cable plus your speaker. So two people with the same cable can report two different phenomena on what they think it sounds like based on what your amplifier is or what your speakers are. So the cable by itself, in a screwy sense, your cable designers are trying to sell you a cable that does nothing as well as they can. But there's no way you can send a signal from one end to the other end of a cable and have it do nothing because we have reactance that alters our voltage and current waveform. So that's the problem with analog. We're death by 1,000 cuts even with our cables. Now here's some pretty simple equations that we can use to kind of cheat. And they let us figure out what our cable's doing at low frequencies. You have capacitance in a cable and you have inductance, but they're both frequency related in terms of what your amplifier is trying to see, and it's called capacitive and inductive reactance. The reason it's called a reactance is because that term is in there, F, frequency. So as your frequency changes, the reactance the amplifier is trying to drive, hence the term reactance, the amplifier is reacting to the load. It's changing all the time, so it's a moving target. Now, if we look at what cable really does, if we test it, does it really do this? This is theory, this is equations, okay? Now, this is actually measurements of a real cable. Let's see if it matches up to what that says is happening. This is called open short impedance. You can't use square root of L over C on an audio cable. You can only use that when a cable looks resistive at RF. So don't think that you get a cheat and use square root of L over C. It won't work. So you have to use a lot more complicated method that involves two sets of calculations. First calculation is open, and that is you take a length of cable and you literally leave the two ends open, not touching together, all right, at all. That's called your open measurement. That's going to capture our capacitive characteristics. In other words, two parallel plates close together is what our speaker cable really is. So you're going to measure the capacitive reactance, and that's going to give you a number. Then we're going to short those two ends together and twist them together. That's going to be a dead short. So that's going to give us our inductance, our skin effect, our proximity effect. All that stuff is rolled into that measurement. So that's going to give us our short measurement. If you take your open number times your short number, take the square root of it, that gives us our impedance at that frequency. But lo and behold, just like the curve showed, our impedance keeps going down, down, down as we go towards RF. That's because the velocity of propagation is slowly becoming more linear as you go out to the RF region, where it eventually becomes the same number no matter what. So if you have polyethylene, it'll eventually reach 66% velocity, stays there forever after. That's what you call the RF frequency range. Analog cables don't do that. They keep changing all the way down to DC, where the velocity of propagation is undefined. DC doesn't have velocity, right? It doesn't pass AC signal at all. That number technically goes to zero, hence anything divided by zero is undefined. So Mother Nature doesn't go right to DC and then straight down. She kind of sneaks up on it. And when she does that, she changes the velocity all the way down to where you eventually hit DC. Now if we look at our phase angle, we have two phase angles, one for the open, one for the short. Well, look at that. What do you know? The spectrum analyzer says, hey, my cable is capacitive. Why do we know that? We know that because it's got the negative sign in front of it. That tells me, wow, at low frequencies then, your speaker cable is primarily a reactive capacitive load. And that's what your amplifier is trying to drive. How many people do much with techie stuff with amps? Anybody? What do you generally do to an amplifier knowing that your load is primarily capacitive? What do a lot of manufacturers do? What they'll do is they'll put inductance to offset the capacitance in the output of the amp. How much do they put in there though? Because they're trying to offset the capacitive effect so the amplifier doesn't oscillate. So inductance is the opposite side of the teeter-totter to try to make that capacitive reactance go away and make it look like it's not there. It's a guessing game because they don't know how long your cable is. The reactance is totally per foot, so it's dependent on the length of your cable. It's also dependent, all right, on the characteristics of the amp itself in terms of what kind of capacitive load it can drive, and add that to what your speaker's adding. So all that stuff adds up to kind of bug the amplifier, because the amplifier really wants to see a resistor. All amplifiers are oscillators given the chance. We had a lab at Purdue 40 years ago, I hate to admit it, and our professor was a sneaky little guy, worse than me. He gave us a circuit to make, and we all had the same proto board, and he gave us a bunch of components. He says, okay, today we're going to take I think it was a 741 op amp, right? 555 was the timer, 741 I think was the little op amp. But it's a little 8-pin op amp. Half of us made amplifiers, the other half of us made oscillators. The half of us that made oscillators flunked the class unless we could tell him how to make it not oscillate. That was the point of the class, is to prove to us amplifiers really can be an oscillator if you make it wrong. What he knew is half of us would use leads that are too long and everything else and add a bunch of capacitance to the output of this little 741 op amp. And when we go to test to see what our gain is, it would just oscillate all over the place. So it wasn't until we cut our leads down short and everything and got rid of all the capacitance and or added inductance did it actually become an amplifier. So again, all amplifiers given half a chance, most of them will tend to turn into oscillators. So we want to get rid of that capacitance primarily. So our big alligator on a speaker cable is really capacitance as far as the amplifier is concerned. Your concern, or the average guy, will think it's the inductance because we're pushing a whole bunch of current down this cable, which is true. Moral of the story, they both matter. So don't believe it when people say low cap on a speaker cable isn't really important because you don't roll off the high end till the megahertz range. That's only one of the things that capacitance can do. The other thing it can do is drive some amps into some instability. Now here's the other problem. On a speaker cable, you're putting a ton of power into your lower frequency range. This actually came from PS Audio. And what this is it's a peak and hold trace of how much power is going through these frequency ranges. And if you notice, you've got like 1,000 watt peaks here, 15 watts in the tweeter, 1 watt. So right where a cable has the most reactance, we're trying to push the most current and power. That's kind of a train wreck, right? But that's what we have to deal with. So the amplifier is trying to work its butt off into a highly reactive load in the lower frequencies. You'll see a lot of people, a lot of guys read stereophile and stuff, and you'll have people say, you know, this amp sounds really good with these speakers, that kind of thing. Well, that's because the amplifier, A or B, deals better with the reactance of the load that that particular speaker and cable happens to be exhibiting. So the changes in the amplifier's linear response goes away once you move off of a resistor. So that's absolutely true that amplifiers can react to cables. So some of you guys may say, oh, I love your cable. The next guy will put it in and say, well, this other brand works better for me. Totally reasonable to say that or experience that. Nothing to see there at all as far as how that might work. Now, here's the other bite of the alligator. It's not just the cable. The amplifier sees the cable plus the speaker, and this trace is the reactive characteristics of the loudspeaker over here. And notice it can be almost purely capacitive at certain frequencies, And these frequencies are way low before this gets high enough to where it starts to kind of try to act like it's resistive. So right where you're dumping the most power, the cable is the most reactive to your amplifier. So this is a problem. All cables do this. No one solved it. You can kind of work around it as best you can by trying to keep the capacitance low while you try to make the inductance low. That's basically the name of the game. Now, some manufacturers will try to make what I call long capacitors, because they'll say, oh, I have the lowest capacitance or lowest inductance speaker cable in the world. To do that, they might take two parallel plates of copper, put a 1/2 mil film on mylar between them, put them together, and that's a long capacitor. You might have 1,800 picofarads per foot of capacitance on a cable made that way. So it's easy to get inductance low if you're willing to take really high capacitance. It's really hard to get them both low. But that's the key, because of what, in my view of my way of designing cable thinking, my thinking is you get them both low, and the reason being, I don't want to make your amplifier oscillate. Have you guys listened to Richard Vandersteen's Model 7s? You should go listen to them, really nice speaker. Now, his amplifiers have no feedback whatsoever. The cable he hooks up to those speakers has to have a certain amount of inductance to offset the capacitive characteristic of his Model 7 speaker. So he's designed a closed system because he knows the speaker cable has to have more inductance than normal so his amps don't oscillate. He feels the advantage to not having any feedback at all in his amps and some other things are advantageous to having a cable that might have higher inductance and maybe not some other properties that might be desirable. So you might get benefit of 2 here, but he feels he gets a benefit of 4 over here at the amp for a net benefit of +2 kind of a thing. So he has a closed system. Perfectly legit way to do it. Don't use a cable that goes outside of his recommendations as a for instance though, because that's a closed system, and for the reasons I've described there, he knows his amplifier doesn't like capacitance, so he has designed an inductance into the cable. A lot of the amplifier manufacturers design it into the amp itself. It's in there, you just don't know it, and they guess at the amount of inductance they need to offset the nominal value of capacitance that you might see on the market. But there's no exact number at any exact frequency. Everything's a little different. Now, when we look at a speaker cable, why are they big and fat? Because we generally have current going through a speaker cable, so we have what are called I²R losses. So we take the current going through our cable, we square it, we multiply it by the resistance of the lead, and that's how much loss is on the cable itself. Well, we want all the signal to get to the speaker, right? Not the cable. So what you do there is you make the resistance as low as you can get it, because if this is 0, 0 times anything is 0, so your cable's not losing any energy at all. It's not turning anything into heat. So an amplifier cable or a speaker cable is a power law device as far as that goes. That's the other thing most people understand with speaker cables is gauge bigger, better. And that's right. And that's the reason why. But it's not just, oh, I just need 10 gauge zip cord and I'm done. You still have to manage the capacitance and the inductance as well, because that's a steady state loss. Inductance is a time dependent loss, and capacitance is also time dependent in terms of what it does to what are called the poles of your amplifier in terms of where it becomes unstable. So a lot of people don't know that there's some other stuff going on behind the scenes that they just don't tell you as much about as you might want to know. Today you might want to know it either, but you're here to find out. Now, what to do? Make your speaker cable short. It's per unit length, right? So the shorter it is, the less everything that's bad is there. So that, okay, we make it short, that's easy. All right, the other thing you can do is some people will put inductance into the output of an amplifier to offset the capacitance. This is done typically in amplifiers. Third thing you can do is use a Zobel network. Now, what's that? That's the same thing they put inside your amp, but it's external to the amp, and usually they put it on the back of your speaker terminals. Some speakers have a Zobel network built in that makes the reactive characteristic of that speaker very low, so whatever your speaker cable might add, generally not as bad as the speaker, by the way, is not enough to really cause a lot of amplifiers to have overshoot or ringing in the audio band. So all the manufacturers know this stuff. They do it. They don't really tell you. All cables and speakers exhibit these properties that have to be tamed a little bit somehow. Now, you can put a Zobel network in a cable. You see some of these cables with boxes in them and things, guarantee you inside there's a Zobel network that tries to make the reactive property of that particular cable at that particular length close to zero. And you can do that by using passive components and hang it off of there. Anybody in the power industry? What do you do with a power plant? You want the resistive load on a power plant to be resistive, right, for your lowest cost? Well, they have a box outside your plant that monitors the average reactance of the load that the power plant's trying to set. Let's say Belden is absorbing tons of power making cable. Outside there's a real-time box that's loading the reactance of the load, and it has a variable inductance on there and capacitor bank that modulates the load being given to our factory, so our power factor is 1, meaning it looks resistive. We're not losing any power due to waste. Anybody put a hand on a transformer, for instance, on an electronic device, that big heavy black box, and they notice they're hot? Why is it hot? You don't get hot for free. That's called hysteresis loss. That's because the power factor going through that transformer isn't 1. You lose power due to the reactance inside that transformer. So the Zobel network is an attempt to normalize that to be as resistive as possible, but we can't do it across all frequencies because it's a moving target and we're using passive components. But you get close. You try to get as close as you can. Now we'll look at our interconnect cable, and we have to realize something. Our interconnect cables, even though they're exactly the opposite of a speaker cable, have a lot of things in common, and sometimes people are surprised by that. Our speaker cable is moving tons of current, and of course the mitigation of capacitance and inductance for a little different reasons than an interconnect cable. Interconnect cable is a voltage transfer function. We're trying to move voltage from point A to point B through our length of cable. How do we do that? When you're working with these voltage transfer functions, you basically are envisioning the cable looking like a giant capacitor. Not a giant one, but a long one. I guess that you keep our numbers small for a reason, so I guess it's not giant in terms of total capacitance. Why would you make the capacitance low in interconnect? Everybody here knows the best interconnect has the lowest capacitance, right? That's kind of the common. So the big alligator on an interconnect cable isn't, all right, the inductance, it's the capacitance. It's just the opposite of a speaker cable. Why is that? First of all, you have this RC time constant, which again is frequency dependent. It's a form of reactance again. The time it takes a capacitor to go from 0 volts to full charge, and remember our cable is just a glorified capacitor. It has capacitance per foot. You can't cheat out of that. It's a capacitor. It's going to take 5 time constants for that cable to reach a full charge, playing any kind of sinusoidal information. It takes 5 time constants for that same signal to drop back down to 0 and start over again. The only way to control that is to keep your capacitance as low as you possibly can. So interconnect cables generally are run with very low capacitance and over relatively long lengths. And how do you get away with the length? We're putting them in a load that's theoretically infinity. The load on an interconnect cable is what? Somebody know? Nobody read stereophile? The load on your RCA cable or your XLR is generally 47,000 ohms, give or take. That impedance is so high that the interconnect cable, if you were to measure the current going through the center conductor, is almost 0. Because it looks like the end of the cable is not connected to anything. It looks like an open circuit. So they make the resistance that cable is going into so freaking high, there's no current. Well, if I take current, okay, E equals I times R, if the center conductor in an RCA cable is relatively high, because let's say it's a 22 gauge or 30 gauge, but if I have 0 amps going through there almost, how much voltage am I losing across the cable? Almost none, right? Because you got 0 current times any resistance equals 0. So the loss across my interconnect cable, no matter how long it gets, is almost nothing. And that's why an interconnect cable can go a long way, is we've kind of tricked it by making it think there's no current going through it. All we want to see at the end of that cable is a voltage transfer function. And to do that, we don't really need a bunch of current. We just need to look at the voltage potential going up and down, and I can do that without current. So basically, we get rid of the current and switch over to deciding I'm only interested in the voltage. The capacitance, though, on that does affect your I/O op amp. Same reason, right? So we still have the load capacitance on an amplifier that can cause ringing or oscillation, because you still have a little amplifier that runs your XLR or your RCA cable. It just doesn't pop out of your equipment for free. You actually have to have a little amplifier, you know, on your preamp or whatever that modulates your voltage from 0 to roughly 1 volt to drive your amplifier to full output. All right, so that's why you can kind of get away with running your interconnect cables a long way, as we trick it to having very low current and we're popping it into a 47K or higher load. Now, if we look at what's similar, well, the physics jumped from my speaker cable straight to my interconnect cable, dagnabbit. I didn't get a break at all. If we look at what our cable's doing at the low frequencies, 44.76, basically saying it's a capacitor. Same as my speaker cable. We go up to RF, we see the phase go down to roughly 2.66. I didn't go out far enough for it to go down to 0. So it's still doing exactly the same thing. Now, someone with good eyes, what's my impedance? This is a piece of 1800F, a pretty typical Belden product, been made a long time. The impedance of that cable is what? 4,808 ohms, point, be exact, what? 458. Everybody can panic. I got a 4,000 ohm freaking interconnect cable. What am I going to do? Nothing. 4,000 ohms relative to infinity is a pretty low impedance. And it's a ratio between the impedance of the cable and the impedance of the load. Now, when we make our capacitance low, guess what happens to the impedance? It goes up, up, and up some more. So when you strive for low capacitance to have a very fast voltage rise time constant, you automatically raise the impedance. But cable designers know that since I'm going into 47,000 ohms, 2,000 ohms is no big deal. It's a good trade-off. In other words, to let that go up a little bit to get the voltage transfer function such that I don't see any ringing or any issues with my T equals RC time constant. And it is R times C, so C is in the equation. So you want to get that number down to make that rise time number small. So this is stuff that cable designers are doing that they don't really talk to you much about, but it's real. All cables do this. I can test any interconnect cable in this entire show, and it's going to do exactly this. Doesn't matter if it's a speaker cable or an interconnect, it's going to look very capacitive at the low frequencies just by the way the physics works on this. Now again, you know, explaining why the high impedance is because also our velocity of propagation, which is driven by, guess what? Capacitance, starts going lower and lower and lower as we go to higher frequencies. This is a trace of 2 different cables. Now this is artificially low by my design work. If I were to take this end of this curve and bring it down here by lowering the capacitance, I would get a more uniform velocity of propagation across frequency than if I leave this up at 66% velocity or 78 or what have you. We don't need that high of a velocity on an analog cable. What we need to do is make the frequencies travel at closer to the same speed at all frequencies, which they clearly don't at audio, because the VP is going down towards DC, where the velocity of propagation is basically undefined. So Mother Nature doesn't do things in a hurry. She's kind of lazy. She likes to make pretty little curves. This looks like a hysteresis curve on a transformer. So we've seen this S-shaped curve in science projects before. Mother Nature kind of likes to do things again and again and again. But this is cable A, this is cable B. You can fiddle with what this transition region is doing, but you can't trick her into not going to 0, and you can't trick her into not going what's called to the RF dielectric limiting velocity of propagation. Nobody on earth can trick that cable into doing that differently. All you can do is manipulate what those curves look like between those 2 points. Now the VP has C in it, and it's in the denominator, okay? And it has resistance in it, and then omega is 2 pi f, so capacitance kind of sneaks in here in various other places as well. So capacitance kind of is a transitory Mobius strip that affects a lot of other variables, not just one. So a lot of times we tend to think in isolation. When you design these cables, you can't do that, because the minute you think you got the lion by the tail, all right, another one bites your ass. and you got another problem. All right, so you got a line on your butt and the tail of one. Which one do you get rid of? Well, you kind of get rid of both of them. So this is a design conundrum that you're sort of stuck with when you design audio cable. So general rule of thumb, speaker cables definitely are usually better short. You definitely like to keep capacitance low so you don't make your amplifier ring or have overshoot in the audio band. Usually they'll oscillate at RF, which is above our audio band, but when they oscillate, that takes a ton of power to do. So they're oscillating while they're trying to play your music. And if you have an amplifier that's oscillating, sometimes they'll get so hot you can't even touch them and you wonder, why is this amp so freaking hot? Well, it's probably oscillating RF, which is not efficient, and the amplifiers can burn up. Some older amps from the old days, anybody have the old Citation amps that had the super wide bandwidth? That was the first experiment to make amplifiers that would be flat out to megahertz. Turns out they would also oscillate if you put disc washer speaker cables on them, and they would just basically fry because they're oscillating at like 70 megahertz, if I remember, something like that. But they would just oscillate. So it is important to keep your capacitance low, even though we tend to think inductance is a big alligator on a speaker cable. Interconnect, definitely want to keep our capacitance low because it's a voltage transfer function. We want to keep that T equals RC time constant as short as possible. It's measured in seconds, but it's really seconds with a whole lot of decimal points and a bunch of zeros. So don't panic. It's not like 5 minutes or something. It's picoseconds. But we still fundamentally, to make those interconnects good, we want to keep capacitance low. All right, so it's a T equals RC time constant, and it also improves your stability of your op amp driving that cable, especially when they get longer and you've got like a 100-foot piece of XLR hanging off an op amp. That's a pretty good length of cable, and they will drive over 100 feet. Some of them will go 200 feet. So it's not like the op amps are real wimpy, but they still like to drive resistive loads to be the most linear possible. So anytime you're adding reactance to the output of any amplifier, you're sacrificing some linearity. There's just no way around it. All right. So good to go there. As far as inductance goes on op amp or on internet cable, we almost have no current going through an internet cable. Should I let it just go out of sight? No, I generally design so that I keep the inductance very low as well. My idea is they both should be close to zero as you can get. All right, but inductance is the minnow on an interconnect, so the positions swap between interconnect and speaker cable in terms of what's the big fish and what's the little one. Okay, so you got current, speaker cable, you got voltage on your interconnects. So that tries to answer the fundamental question of people saying speaker cable short, interconnect cable long. So does that help you guys kind of understand a little bit why they do what they do with these things? And this is true for all cables. This isn't ours. It's just how the physics kind of pushes you around when you try to work with these things. Any questions?
The interconnect cable is still better short.
Any cable's better shorter because it's per unit length, yes.
There's no reason you would make the interconnect longer just for the sake of it.
No, there's no benefit to making it longer. Now, digital, there's a problem what's called, at RF, you have what's called return loss, and you have what's called SRL, structural return loss. This is a little confusing. Hear me out, it's not that bad. When you design an RF cable, which is non-analog, because our impedance is changing with frequency, so there's no such thing as, well, there's a such thing as return loss on analog because impedance is never the same into the load, which is varying all over the place, so it's a cat fight on impedance. There's no such thing as impedance matching at audio. The stuff's going everywhere, right? So we looked at the impedance curve of a speaker, we looked at the impedance curve of a cable. No, those aren't going to match. So going to audio or RF where it's easy, where they're supposed to match, I can have a 75 ohm resistive load for, let's say, a coax cable, or 100 ohm if you want to do Ethernet cable. My cable plugs into that that's supposed to be the same impedance as that resistor. But the structure of the cable has perturbations in it that make it nominally 75 ohms plus or minus some amount, 5 ohms, 10 ohms, 20 ohms, depends on the quality you want to buy. That's called structural return loss because it's in the structure of the cable, so that's SRL. When you plug that cable into a fixed resistor, that turns it into RL because my load doesn't change anymore, so you're measuring how that cable swept into a fixed load affects the signal transfer. In other words, how much energy is being bounced off of that load because it's not matching my cable anymore. Now you can cheat, and people have done this. What if I make that fixed resistor that's supposed to be 100 or 75 ohm fixed, and I make it variable? I put a little trim pot on it, and I turn that little trim pot until I get the absolute best return loss into this fixed ohm load as I possibly can. Then I advertise the cable as having minus 28 dB return loss instead of minus 23. What's wrong with that? I tricked it into going into a 70 ohm load, but when you buy it, you plug it into a 75 ohm because it's a surface mount resistor on your NIC card or whatever you're plugging it into. So you're not seeing the minus 28. You're actually seeing what the cable is really doing. So the structural return loss is built into the cable. Return loss comes from how it interfaces with the load. So there's a difference between SRL and RL. So be careful, you RF guys or anybody get dabbling around on that. Make sure you're talking about the right variable. You might get gypped. So what you want is good return loss because that's how the cable behaves into the load you're going to use it with. Don't worry about SRL, it'll fix itself. If you have a return loss figure that's minus 28, you're good to go, because that automatically means that cable has a good structure, or you couldn't get minus 28 out of it, all right? But if someone comes up to you and says, you know, your return loss is minus 23, that means you're probably buying a cable that instead of being plus or minus 2 ohms or 1 ohm, it's plus or minus 5 or 10 or 15 ohms. So there is a difference in what's called structural return loss and return loss. Okay, the length of the cable doesn't matter, by the way, because it's the reactive component of the cable. So if I double the reactance to 2 and I double this to 4 and I double this to 4, this goes to 8, so on and so forth. So the vectors, they just keep going bigger and bigger, but the ratio between them is always 1 to 2 or 2 to 1, however you want to look at it. That's why the length of the cable doesn't matter, because the impedance is the ratio of the real component and the reactive component. But an RF cable is supposed to be purely resistive. Our analog cables that we use on our equipment at home, it's pretty much a cat fight. You got to really work it out. You got to make compromises and do the best you can and look at where the most power is being distributed. You know, and amplifier designers know this too. Speaker guys know this too. This is not a secret to those ends. The guys on either end of the cable know the problems. The guy that makes the cable should know the problems. So the idea is to make the cable as close to a zero problem as you can. That allows our analog to have bigger problems elsewhere and not impact the sound that we like to hear. So again, the speaker cable guy's job, or the cable guy's job in general, is to try to sell you nothing. So you're paying for a bunch of nothing if you get a really good cable. What a deal. Sign me up. But that's how it is. So. It depends on the wavelength. Too short is generally bad with digital. Ethernet cable, 328 feet, right? But as you go shorter and shorter in length, you can get a lot of back reflection in the cable because of the power of the signal. It's designed to go 328. So if you're only going 10 feet, you're really slamming a lot of energy back and forth in that cable across that load. And a lot of loads don't like that. Fiber optics, for instance, you have to put attenuators in line with them 99% of the time coming from the pedestal into your house, because the signal is horrendous even on a 10 micron fiber. So they'll put an attenuator in there on purpose to make the signal like 20 times lower than it would be if you didn't put that attenuator in there, because it'll make so much reflections in that fiber optic cable that it will actually damage the transmit laser that's modulating the data. So a lot of people don't realize that, yeah, you get fiber, but they automatically make the signal 20 times worse, so it works. It wants to go from here to Los Angeles, not from this curb to your house. It's overkill. So they have to attenuate that signal. With copper cable, same kind of thing, not as bad. So yes, a lot of times to get a cable to work, you make it longer. Very seldom does it work better making it shorter with digital. So if you have a problem with digital for some reason, dropping out or doing something weird, buy a cable that's twice as long and see what happens. Trust me, your bit error rate is going to be minus 10 to the whatever. It's going to be non-existent with Ethernet. Ethernet will have bit error rate that's in the millions to 1 at 328 feet. So making your digital cable at home 6 feet long instead of 2 feet, no problem. No problem. Any more questions?
And then what's your advice? Because on the internet, everybody has their own opinion on the size, the gauge of your speaker.
Well, I kind of explained it. With a speaker wire, it's I squared R losses, so bigger's better. Always. Yeah, well, it's just a simple voltage divider rule. The lower the resistance of your speaker cable, the more the load gets to the end where you're trying to use it on your speaker. The idea is not to heat up a cable. is to get it to the speaker. So you want that I squared R loss to be as low as you can get it. The other thing is to make the signal distortion from reactive current time-based shift and voltage time-based shift as close to 0 as you can get. Because you don't want to distort the signal either. So you want a good signal to get there, and you don't want it to distort it either, and that's where the L and the C come in. A resistance won't distort the signal. It'll just make it smaller, but it won't be distorted. No problem, but the L and C will distort it. T equals RC time constant matter on a speaker cable 2, and of course the reactance makes your amplifier less linear, unless you listen to a resistor at home. I don't. Yeah, it's digital, high frequency digital, yeah. So, did it work? Did everybody like it? Learned something today? A little more than you wanted, probably a little more complicated than you thought. But a lot of the stuff is figured out for you. When you buy an amp or a speaker, the Zobel networks and the inductive loading, you don't have to do that. So long as you buy a cable that's reasonably normal and capacitive and inductance. Now some of these crazy cables that are like 0.01 inductance with 1800 picofarads per foot, better check with your amplifier manufacturer and the like to see if that amplifier is going to be aggravated by that much reactance based on the length, for instance. So there are cables out there that are just long capacitors, and their claim is true, very low inductance, but you can't use them on speakers with very low negative feedback and things like that, because that feedback's designed to help manage that phase shift that's caused by the reactance, because reactance is basically phase shift. And that Laplace transform pole that determines when an amplifier oscillates gets closer and closer to audio, the higher and higher that reactance is, and it'll actually cause ringing in the audio band before it full-blown oscillates. That's generally above the audio band. But I sent my cables to Richard, he asked about it, and I said, well, our cables are to be low inductance. You can test them and see. And he tested them, and sure enough, there was ringing. So he had to have a cable with more inductance than ours. Our cables were too good for how he designed his system. So we've been told to skedaddle. So my big mouth got